this episode of Remote Trigonometry, we will be going over some examples of linear speed and angular speed where gears affect each other. Here we have a bicycle, and a bicycle is a prime example of a machine in which gears affect each other. When a person pedals this bicycle, they're moving around the bigger gear that's connected to the pedals. For this particular bicycle, that gear has a radius of 10 centimeters. If a person is pedaling 24 revolutions per minute, or RPMs, that means that that gear is going around 24 times every minute. The circumference of that gear is 2 times pi times its radius of 10, or 20 pi centimeters. So every time that gear goes around, it's tracing a circumference of that gear. So if it goes around 24 times, then it's tracing a length of 24 times 20 times pi, or 480 pi centimeters per minute. That is its linear speed. Linear speed just means length. It just means length per time. So centimeters per minute, miles per hour, kilometers per hour, inches per second, all of those are examples of linear speed, a length over a time. So again, for this gear, its circumference is 20 pi centimeters. If it's going around 24 times every minute, then it's tracing a circumference 24 times every minute. And so 24 times 20 pi is 480 pi. The unit was centimeters, so centimeters per minute. That is affecting the chain. So the chain is moving at the same speed as a point on that gear that's connected to the pedals. So the speed of the chain is then affecting that little gear that's attached to the back tire. That little gear is moving at the same linear speed as the chain, which was moving at the same linear speed as the bigger gear. So the circumference of the smaller gear is 2 times 4.5 times pi centimeters, or 9 pi centimeters. And so that circumference has to fit into the speed of 480 pi centimeters per minute for us to figure out the revolutions per minute. Don't try to really memorize that. Instead, look at what the units tell you. If I take 480 pi centimeters per minute and I divide by 9 pi centimeters, notice the centimeters cancel out. In this case, the pi's also cancel out. And I get 53 1/3, and it's revolutions per minute. So notice the per minute was left, but what were we figuring out? We were figuring out how many times that smaller circumference fits into that speed. And then that's giving us the RPMs of that little gear that's attached to the wheel. So the little gear is spinning 53 1/3 revolutions every minute. Well, guess what? It's making the whole tire go around 53 1/3 revolutions per minute. And so the tire is also revolving at that same RPM. So if I take 53 1/3 and I multiply by 2 times pi times 29 centimeters, that will give me the linear speed per minute of the tire, and that's how fast the bicycle is going. So if we multiply together 53 1/3 times 2 times 29 times pi, we get 9,717.99, but the units are centimeters per minute, okay? So that's how many centimeters per minute. I guess I'll just put the 0.99 since I already wrote the 0.7, or I could write the 0.8. So anyway, that's centimeters per minute. Well, if you were talking to somebody, it might be more meaningful to them if they understood how fast the bicycle was going in kilometers per hour, because kilometers are kind of close to miles. So let's convert this to kilometers per hour. So I have centimeters per minute. I want kilometers per hour. So 9717.99 centimeters per minute. There are 60 minutes in 1 hour. So notice if I multiply by the fraction, 60 minutes over 1 hour, the minutes cancel. And then I want kilometers and not centimeters. So there are 100 centimeters in 1 meter. And there are 1,000 meters in 1 kilometer. So the meters cancel and the centimeters cancel. I'm left with kilometers and I'm left with hours. So if I take all of those numerators, 9,717.99, and I multiply by 60, and I multiply by 1, and I multiply by 1, and again my unit is kilometers now. And in the denominator, I have 1, there's 1 there, times 1, times 100, times 1,000. I will end up with 5.83 kilometers per hour. Again, that was all of the numerators, the 9,717.99 times 60, and then times 1, times 1. I didn't put the times ones because we didn't really need them. And then in the denominator was 100 times 1,000, so that gave me 100,000. And if you complete that arithmetic, you get 5.83 kilometers per hour. So that is how quick the bike is going. Again, not too quick of a pace. It's a kind of a leisurely bike riding pace. All right, so we have figured out that our bike going 24 revolutions per minute with a pedal gear of 10 centimeter radius connected to a smaller tire gear of 4.5 centimeter radius connected to a tire of 29 centimeter radius will end up going a speed of 5.83 kilometers per hour. Here we have a simple machine with a small gear turning a bigger gear. The small gear is spinning at 50 revolutions per second. It has a radius of 3 centimeters. So a point on that small gear is going around 50 times every second, or tracing a circumference of 6 pi times 50 every second. So again, where I got the circumference is the circumference of a circle is 2 times pi times the radius. So 2 times the radius will be 6. 6 times pi is the circumference. That times 50 will give me a linear speed of 300 pi centimeters per second. Again, that 300 is 50 times 2 times 3 pi. So 2 times pi times the radius is the circumference. That's the circumference. That times 50 is how many times it's going around. So the linear speed of the little gear is the same as the belt, is the same as the big gear. So the linear speed of all of those is 300 pi centimeters per second, or about 942 centimeters per second. If we went the angular speed of the big gear, then we have to figure out how many times that big gear is going around. We know that the linear speed, meaning a point on the big gear, is moving 300 pi centimeters per second. So if we divide the circumference of the big gear into the linear speed, we will get what the revolutions per second are. So 300 pi centimeters per second divided by 18 pi, remember the radius was 9, so 2 times 9 is 18 centimeters. The centimeters cancel, and I end up getting, it'll be 16 2/3 actually. That's how many revolutions per second the big gear is moving around. So if you wanted the angular speed, then you're going to take a full circle, or 360 degrees, times how many times this is going around. So if I'm going around 16 2/3 times per second, multiply that by 360, and that's going to give me how many degrees per second. So angular speed is degrees per time, or radians per time. If I wanted to work with radians, I would use 2 pi radians, because that's a full circle instead of 360 degrees, which is a full circle. And it's still going around 16 2/3. And if I multiply 2 times 16 2/3, I get 33 1/3. So anyway, that's probably about 104. Yes. So the radians were 2 pi times the 16 2/3. So I took 2 times 16 and 2 times 2/3 and got 33 1/3. That times pi is approximately 104.72 radians per second. So 33 1/3 radians per second, which is approximately 104.72 radians per second. So again, let the units tell you what you need to do. Angular speed is degrees per second or radians per second. Linear speed means length, so centimeters per second or inches per minute or miles per hour.